Hello. Okay, so my name is David Vorrick. I've been paying attention to Bitcoin and cryptocurrency since 2011. I'm the lead developer of Saya, a decentralized cloud storage platform. And I bring that up because I come from the coin developer side of the world as opposed to the hardware side of the world. So as I work with hardware, I'm constantly thinking of it from the terms of coin devs and what we care about when we build cryptocurrencies. And I'm also the Obelisk CEO, which is a cryptocurrency ASIC manufacturing company. And so I was asked today to talk about cryptocurrency ASICs. And so that is a really broad topic. And the format that I've chosen is that I'm just going to blast through as much as I can. And I'm going to try and leave some more time for Q&A at the end. And kind of have something closer to an open forum. So hopefully we'll get like 10 to 15 minutes of Q&A at the end. And so yeah, we'll see how it goes. So I think the place to start with ASIC manufacturing would be at the foundry. So a foundry is a company that is capable of manufacturing or is actively manufacturing cryptocurrency ASICs. And then you have these things called fabs, which is essentially a facility that is capable of manufacturing ASICs. So there are just a couple dozen foundries in the world, maybe 100 fabs. And then as far as, so within a foundry or within a fab, you have these things called processes, which is essentially a methodology for building a chip. And these processes have names you might recognize like TSMC 16 nanometer or Samsung 7 nanometer. And as an aside, the name 7 nanometer or 16 nanometer is less a description of the process itself. For example, 7 nanometer is like really your feature size is in the 40 nanometer range. Instead, when TSMC says 7 nanometer, what they mean is this is the thing after our 16 nanometer version. And 16 nanometer itself, was after the 28 nanometer version. So you can nano marketing is a term I've heard before. But it is a pretty good indicator of which level each thing is relative to the other levels. So in cryptocurrency, there are really only two foundries that matter, which is TSMC and Samsung. There are other foundries that are sometimes involved, but for practical purposes, it's mostly TSMC and Samsung that we care about. And then pretty much everything is at either TSMC 16, Samsung 14, or some more advanced node. And so if you see 28 nanometer or 65 nanometer, generally that's not going to be a cryptocurrency ASIC, at least not a competitive one. So after you have a relationship with a foundry and you know what process you're targeting, you have to do chip design. And so generally the foundries aren't the ones who design the chips. You have chip design houses or chip design teams that come together and they decide what circuit or what physical structure the foundry is going to assemble, and they pass instruction sheets off to the foundry, and the foundry uses that to assemble manufacture your chips. So there are two major design methodologies. One is digital, one is analog, and I'm going to break those down. So digital design is what most of the industry is today. It's what you use to make CPUs, what you use to make GPUs, AI, machine learning chips are all digital design. Digital designers work with ones and zeros. They work with, like a standard library of full adders, half adders, XORs, ANDs. And so they're not really working at the physical level of the chip. They're working at this abstraction layer, kind of like a programming language, and they'll often program in Verilog. And so then they use a tool called place and route to take their high-level gate designs, and then that tool will translate it into a physical design on chips. The advantage of this is that when you're not worried about currents and resistance and all these physical features, you can move a lot faster. And so that's why pretty much everyone today uses the digital design methodology, is because if you were to use analog, it'd just be too slow. So most chips today are quite complex and are really only possible using digital design. Analog designers don't really work with gates as much as they work with signals and physical features and it's like a lot more intense and a lot more hands-on, and it's a lot slower. However, because instead of thinking about gates, you're thinking about the actual wires connecting the gates together, the actual like fins on the process, you can do a lot more optimization. So analog chips tend to be a lot better, but they take a lot longer. And so even, I forgot to say, a complex digital design might take 1 to 2 years to make. A simple digital design might be 2 months, or even just a few weeks if you have a highly coordinated and pipeline process. But in analog world, simple chips will take 6 to 12 months, and complex chips are just not feasible. The whole industry will have moved on to new processes. We'll be at 3 nanometers before you finish an Intel CPU in an analog design, for example. So in the cryptocurrency world, it's pretty much mostly analog, actually. So all Bitcoin chips that are competitive are analog, and that's because the SHA-256D circuit is relatively simple, and it's also a static target. So for example, in the GPU world, NVIDIA is not trying to make like a theoretical GPU. A GPU is trying to hit a target set of use cases, and as the world grows, that set of use cases is a moving target. If you're spending too long optimizing a chip, it doesn't work. In Bitcoin, SHA-256D is not a moving target, it's static. And then on the ASIC resistant side of life, that's mostly digital. It's usually about getting to market fast. Usually you're going to be bricked anyway. So you don't spend as much time optimizing, and you more worry on the digital or on the ASIC resistant side of just being fast. And for that reason, a lot of ASIC resistant chips end up being digital, or they're just too complex. So now I'm going to take you through a couple of like layers of optimization that you can do in chip design. So the biggest and like most classical would be algorithmic optimization. And I think a good, this is something that anyone in software can do. A good example would be early termination in Bitcoin chips. So in SHA-256D, you have 128 rounds of SHA that you have to do. You get a result. You look for a bunch of leading zeros. But actually, if you work backwards, there are enough leading zeros that you can work backwards through the SHA algorithm, and it becomes apparent as early as like round 121 whether or not you got all of those leading zeros. And so there's no reason to do all 128 rounds. You can usually quit at 121, and that's an algorithmic optimization. The next level down, you do circuit level optimization. And so I'll use the adder as an example. So if you're adding two 32-bit numbers together, there are maybe 20-ish. It's a large number of different commonly used ways to add two numbers together. And some of the methodologies will give you a chip that is very energy efficient. Some of the methodologies will give you like an adder that is very tiny. And in the chip world, area equals money. So you like small things because it saves you money. Some of them are very fast, so a circuit optimization would be looking at like all the different things that your chip is doing and all the different maybe high level or business goals that you have, and picking the types of circuit constructions that optimize for your end goals. So once you have your circuit, the next thing down would be place and route optimization. In the digital world, sometimes this means that instead of letting your chip compile for 3 days, you let it compile for 2 weeks. And it just takes more time and tries to optimize better. If you're going to go into the analog world, that's where you start to do hand routing. And so you'll have designers who will just place the wires by hand and try and figure out the best way. And usually, the people doing it by hand will be 2 to 5x better than what the machine can do. Although there are situations that are much more brute force, and of course the machine is better at just brute force optimizations. So if we go down one step further, even in the analog world, designers will often use standard cells. And so you have your XOR gate or your NAND gate, or I'm going to use a half adder today as my example, which has 2 inputs and 2 outputs. And generally, the foundry will give you a set of cells, somewhere between like 30 and 90, depending on the maturity of the process, cells that you can use that are pretty general purpose. And so they have reasonable trade-offs between how much electricity they consume, how fast they are, what voltages and temperatures they can run at. And so they'll be qualified in a certain range of physical conditions. If you know that you are going to be running things at low voltage, for example, most foundry cells will be qualified at around 0.6 volts, Bitfury, I believe, runs their chips at 0.27 volts. You can't use the foundry standard cells anymore. You have to make your own. And so you can actually take these XOR gates, and you will, at this level, you are taking physical features of the chip. You're talking about fin distances and just other really physical stuff, and you're running simulations that are trying to emulate physics to optimize your gates. And so if you want to get into the Bitcoin world, you're going to have to actually do some standard cell optimization. This is a place where it's pretty rare that people get involved, although I do think most of the major AMD, NVIDIA, Intel all do standard cell optimization for their chips. So one of the things that's like really interesting to me is that I saw a spec sheet for a half adder, and it had different timings depending on what the inputs were. So if you have a 1 and a 0 as an input, the time it takes for the computation to complete is going to be different than if you have a 0 and a 1 for an input. And also the amount of power that it consumes is going to be different. And so if you know that within your circuit you have a lot of gates where you really need to reduce the time that you get the second output, the second input's going to be really late, and you need the second output to be ready as soon as possible, you can actually reconstruct the physical components of your gate to optimize that. So once you have your chip laid out, you have all the optimizations in place, you're ready to go, you do something called tape out. You essentially, you produce something called a GDS, which is like a bunch of images. Your chip is a bunch of layers, and so you'll have a different image for each layer of the chip. That image is something that the foundry can turn into manufacturing steps. They make these things called masks, which are essentially, for a single chip, you might have between 80 and 150 really high purity pieces of glass with chrome on them that etch out these really fine-grained features. These masks genuinely cost millions of dollars. The precision is extremely high on the chrome etchings, and the glass is very pure, and there's a fair amount of them. But basically, after you tape out, that's like the chip is complete and the actual manufacturing is started. So a big element in cryptocurrency is turnaround times. And so one of the big turnaround times that you really need to focus on is the time between taping out, the time between sending all of the instructions to the foundry, and the time that you get your first chips back. And so at 16 or 14 nanometers, this is going to be typically between 75 and 100 days. And that's something that you really look to optimize over. Some of the, I don't know if I would use the word sloppier, but some of the less sophisticated foundries will have longer turnaround times at the same process. And so that's one of the reasons that TSMC and Samsung become really important, because they can be days or weeks faster than the competition. And in ASIC races, every week counts. So on the whole, if you're doing a simple digital chip, you can get a design done in maybe 2 months, 2 to 3 months. If you already have a design completed and you're just tuning it to match a new algorithm, you can get it done in as fast as 2 weeks. And then you have to tape out. If you're taping out at 16 nanometer or 14 nanometer, it's going to cost you between $3 and $5 million. That's just to make the masks and to get the foundry interested. And so in total, a really streamlined process, at least at 14 nanometers, is probably going to take around 6 months. If you have a more complicated chip design, the design phase is going to be longer. And so that's going to push your timeline out. So beyond chips, you have the machine construction. And just to highlight the importance of it, if you, the Bitmain S15 chip, if I read the spec sheet correctly, is capable at standard operation of doing 42 joules per terahash, which sounds insanely good, but then when you put it in a rig, when you put it on a hashing board and connect it to a power supply and plug it into the wall, you add the overhead of the fans and everything, their whole machine is actually running at about 57 joules per terahash. So they're losing something like 35% from the chip to the wall, and this is a highly sophisticated machine. And so I say this because we've seen a lot of people trying to compete with Bitmain, where they'll get a chip down to, their chip level efficiency will be similar to what the S9 efficiency is for the whole rig, and they'll miss the part that they're going to lose another 40% power when they put that chip onto a board. But that's Bitmain's at the head of the industry, and even they're losing as much as 35% power. Another thing that Bitmain's been really good about, one of the big innovators in the space, is cost reduction. So a traditional approach to put 63 chips on a board might cost like $5,000 per machine. So if you were to give a standard designer like 189 chips and tell them to put it on a board, they might give you a BOM that comes back at $5,000. But Bitmain, I would estimate for the S15 is closer to $1,200. This is of course not publicly released information, and I don't have any inside source or anything. That's just my appraisal of what it probably cost them to produce the thing. And that is just something they've spent a lot of time optimizing. So this is the part where I'm going to open the floor to questions. If there's not too many questions, I'll just ramble about these topics. But these are more things that I wanted to put into my presentation, but felt that I'd rather open the floor. So if we could have people line up.
Yeah, so we can take questions here. Was curious, like, what your perspective is. I've heard that in industry there's kind of a trade-off between chip size and failure rates, and kind of like the variance in you can do a lot of little chips, and your whole board isn't going to get nuked if like a couple of them fail, versus like having a more efficient, larger chip, but you have a higher catastrophic case.
Yeah, so it's actually, yields are less of a problem in the cryptocurrency industry. So in the rest of the chip industry, you got these CPUs and GPUs, which end up being pretty big. Chips are really hard to make, and if you have like one atom of contaminant in your chemical bath, then that might result in one bad chip. And so just lots of chips come back poorly. If you have a bigger chip, the chances of one of your transistors being broken go up, and the chances of that being a critical transistor go up. In the cryptocurrency industry, because our designs are like a SHA-256 ASIC isn't one SHA-256 like engine. It's like a bunch of them. And so if one transistor goes out, you're maybe out like 1/30th of your chip is not performing anymore. So yields tend not to be an issue. When you see cryptocurrency manufacturers go for really tiny chips, it's for heat, because we have some of the hottest chips in the world, and you can't cool. If you were to put it on a big die, it would just overheat.
So one of the things I've been wondering about is why are we using ASICs instead of FPGAs? Because there's a turnaround time advantage to an FPGA in that in 24 to 48 hours you can adapt to a new algorithm, and they also run extremely fast and are very low power. So what are your thoughts on that?
Yeah, so FPGAs are typically between a factor, I want to say it's like a factor of 100. It's 10 to 100 behind an ASIC. So if there's no ASICs on the market and everyone's FPGAs, that's good, and you can come to market a lot faster. But the moment that first ASIC shows up, the FPGAs are done.
I was wondering if you had any thoughts on the PROG POW proposed algorithm for Ethereum and whether that's going to be successful in resisting ASIC development.
Yeah, so I have a disagreement with the PROG POW proponents. I believe that there are lots of corners for optimization. I believe that when NVIDIA or AMD makes a GPU, they have a wide range of considerations that they have to care about, and when we're making cryptocurrency mining machines, we have a much narrower range of things we care about. And every time you reduce the scope of things you care about, for example, NVIDIA wants a certain level of yields. They want their chips to be running fine at a wider range of temperatures. If we have to mandate that our data centers keep the chips, at 80 C or 90 C, this is kind of already a mandate anyway. And so I think that ultimately, there will be, if PROG POW gets adopted by Ethereum, I think there will be PROG POW ASICs. And then it's an open question whether it'll be like 3x, 8x, or like a 25 or 50% improvement. But I think you'll definitely see them.
I'd love to hear more about selective hard forks, what they are, what you think the degrees of freedom are for designing for those.
Yeah, so selective hard forks is a really interesting thing that I originally heard about from Greg Maxwell, which is basically when an ASIC manufacturer makes an ASIC, they add a little surprise gate in there. So they add a switch that they can flip. And so instead of mining SHA-256D, you're mining SHA-256D prime. And the difference is like 3 transistors. But to everyone else who's trying to guess which 3 transistors those are, as the manufacturer, not the devs, as the manufacturer, you add that in and you keep that secret. And then if the devs ever end up in a situation where there's some bad hash rate on the network, someone's using ASICs to 51% or something, you can take that extra little circuit to the devs and you can say, if you hard fork to this thing, all of our ASICs will still be mining, so you don't have to fall back to GPUs, which that's a longer discussion. GPUs are insecure, and I'll drop that there. But so you can fall back to ASICs without having to fall back to GPUs. You can break the bad guys without the good guys being broken. And if every manufacturer makes a little different carve out, you can actually, the devs can choose which manufacturers that they keep. And so if the devs have identified exactly which manufacturer is the bad actor, they can break just that manufacturer and leave everyone else alive, which is a political nightmare. It's politically very intense to do something like that.
Hey, thanks for doing the talk. Found it pretty interesting. So this is not specifically relevant to your talk, but I'm wondering what your opinion is on ASIC resistance, and if you think it's something that's sustainable in the long run. Do you think that there are any proof-of-work algorithms that can successfully defeat ASICs just by virtue of their general design? And thirdly, I know I'm piling these on, do you foresee commoditization of ASICs becoming practical?
Sure, I'll take the questions. So if there is to be an algorithm that is ASIC resistant, the strategy used by the ProgPow team is the most effective strategy. That said, as I kind of said earlier, I don't think it's sufficient, and I don't think ASIC resistance is possible. I think ASICs are inevitable. There's one strategy that is working right now reasonably well for some coins, which is to hard fork every 6 months. For over a year now, there have been at least 2 cryptocurrency ASICs, general purpose cryptocurrency miners in development. I don't know what the status is. I don't know when they tape out. But those will be better than GPUs and will be able to follow hard forks every 6 months. So the strategy, it's currently sound. We don't know how much longer it's going to be sound, but my guess is 2 years at most, probably 1 year at most.
So you don't really think it's sustainable for these coins to continuously fork or attempt to remain resistant?
No, I think that we got maybe another year of being able to depend on getting rid of ASICs reliably. And then commoditization. I do think that we will see commoditization of the really big coins. So once you get over $1 billion block reward per year, you get into the territory where margins are no longer so slim that there's just one monopoly, one winner, and nobody else can afford to enter the market. And so at least for Bitcoin, and we're already kind of seeing that, you're going to see more and more ASICs come out, and that's going to, as these manufacturers have to compete with each other on even footing, that's going to even things out. But even Ethereum is not at the block reward required to see that happen, I don't think. So all the small guys just have to deal with monopolies.
Thank you for your presentation. You talk about lots of ASIC things, but I'm a little bit wondering about how your PCB is designed, how many additional chips, gates, and resistance capacitor you need, or how big is your ground?
Yeah, so PCB design is super interesting because I think there are a lot of optimizations that the cryptocurrency industry has done. For example, in standard design, you take a buck, you might, your voltage, your input voltage will be 12 volts, and you're running all your chips in parallel, so you shift that down to say half a volt or a quarter volt, and when you do that, you lose a lot of power. Also, you add a lot of current. So you're gonna, if you have 60 chips on your board, you might have 2,000 amps running through your board, which is not reasonable. So what you do instead is you run your chips in series, which adds all sorts of engineering problems and noise and a lot of headaches associated with running chips in series. But instead of 2,000 amps, you're dealing with 50 amps. Instead of 88% electrical efficiency on the voltage step, instead of stepping from 12.5 to 0.5, you're stepping from 12.5 to 10.5. That might be 97, 98% efficient. And so you save tons of money, you save on electricity, And then you just do a lot of creative things, both chip side and PCB side, to manage the string problem. That's like one of the fun, interesting challenges in the PCB world.
Hi, David. Thanks for your presentation. I actually wanted to piggyback on the question in regards to the hard forks every 6 months. And I wanted to specifically ask if you would comment or voice your opinion on cuckoo cycle for GRIN in the ASIC resistant and ASIC targeted proof of works.
Yeah, so I think GRIN just made it. So I think that we're still at a point where hard forking every 6 months is probably going to be okay for their ASIC resistant side of things. I also think that the GRIN, so right now we're seeing like a nice hash problem. If your block reward is small enough that nice hash can point all of its GPUs at you, you're going to get 51% attacked and exchanges are going to get double spent. GRIN, and I've been watching, seems to be outside that threshold by not very much. And just because you make more money as a GPU miner by being on nice hash most of the time, that problem is going to get worse. But at least right now it seems like GRIN is ahead of the curve. And so I think, again, this isn't a strategy I would recommend that people replicate a year from now, but it seems like it's going to be okay this time.
Thank you.
Hey, my name's Alex. Why chips? Why not whole wafer custom interposer ASICs?
Yeah, so for something like SHA-260, there's no reason to do interposers. For something like Cuckoo-231, when you got all this memory that you have to deal with, then interposers do make sense.
No, my question is why break the wafer at all? Why not whole wafer ASICs?
I think because you just can't. I don't think the way that foundries work. I don't think you can make whole wafer ASICs. So you have this thing called a reticle. It produces a cut on a wafer that is 25 by 35 millimeters at most, and then your whole chip has to fit inside that little tiny square. And so that's why GPUs don't usually get bigger than 600 square millimeters. It's because the actual, the masks that we make don't do a whole wafer at once. They do a little tiny square 100 times. And then I don't think it's possible to connect the circuits between them. The precision on the stepper motors is not high enough.
Hey, I'd love to hear your thought on the difference when you design a chip which is for memory bound versus compute bound. Is there significant difference between the two?
Mimblewimble versus?
At hash for Ethereum, which is memory bound, or a SHA-266, which is CPU bound. When you design the chip, is there specifics when you want to design memory bound proof of work chip?
Yeah, so I think every chip is its own fun challenge. The trade-offs that make sense are going to be different, and we've looked at things like ProgPow, Ethash, obviously Cuckoo, and for everything, the optimal memory architecture is going to be different. And so basically, it's just like a bunch of engineers in a room beating ideas against the wall and trying to figure out the most efficient way to get the data from one place to another. And get the computation done. So I think with any memory hard chip, you're just going to end up with a custom memory architecture that has to be refined over time.
I have two questions. One of them is, do you see any hope in alternative proof of somethings around memory size or other expensive operations that don't require spinning transistors through computation?
I do not.
Okay. And then the other, that's fine. I kind of thought so, but I just.
Okay. Yeah.
And then the other one was, do you have an opinion about, in moving from proof of work to proof of stake, miners revolt, economically this is a big break function if that actually is working out from a miner perspective?
So that's a great question. I actually had a first slide that I took out, but this is my first slide. So with proof of stake and really any pre-proof of work consensus algorithm, you have to pick I'm going to use the word trusted setup. You have to pick a trusted setup. There's a set of keys or identities or signatures that govern all the rules. And so you have this tight little bounding box. And the goal is to get it so that tight little bounding box can grow and change and morph. But ultimately, it's a trusted setup, and you don't really have any great way to verify that, the state of that. Proof of work provides this great tether between the physical world and the digital world, and so we get to blow that bounding box up to all of physics. So if you have access to raw materials and lots of know-how, you can make your own transistors, you can make your own CPUs. And so I'm not a fan of proof of stake for a large number of reasons. I think on many sides it has significant issues with it. And I think that proof of work really is like super revolutionary, and it's like the best way forward.
Thanks for the great talk and Q&A. So let's thank David for this.